In this lesson, we'll begin a new section on hardware, which is Unit 15 of the syllabus. Now, if you ever wondered what the difference was between an Intel i7 processor and an Apple M1 processor, this unit hopefully will address that particular type of question. We're going to be looking at the different design philosophies behind processor development, RISC and CISC. And in today's lesson in particular, we're going to be looking at the importance of using pipelining and registers in RISC processors. We'll hopefully also understand how interrupt handling works in RISC and CISC type processors and how it is different from just the normal interrupt handling we've been covering so far at IGCSE and AS level. So to me, this is one of the basics of computer science. If you ever want to go into perhaps hardware architecture, electrical engineering, processor development, then this will be the starting point for that particular journey. And if you enjoyed assembly language last year and logic circuits, then this will build upon those aspects of the course. Now, as always, let's begin with a prior knowledge check. On screen, you will see a few questions. Pause the video and try to think or find out the answers for these. So what are processors? What are the stages of the fetch execute cycle? Do you remember those? What is meant by a register? What is an interrupt? And also what is meant by an instruction set? Okay, hopefully you worked out that processors are basically electronic circuits which allow you to do calculations or computations. The fetch execute cycle should be pretty straightforward. The program counter contains the address of the next instruction. The address is copied into the MAR, then it's transferred via the address bus. You take the data, which is transferred via the data bus, into the MDR. From there, it's transferred to the CIR, and then decoded, executed. The whole cycle begins again as the PC is incremented. You should have worked out something along the lines of that. Now, a register is basically a temporary component in the processor, which can be general or specific, and it holds data or instructions as part of the fetch execute cycle. An instruction set, on the other hand, is the complete set of machine code instructions which are used by a CPU. And finally, an interrupt is a signal sent from a device, hardware, or software to a processor requesting its attention. And normally the processor will suspend all operations until the interrupt has been serviced. Now, if any of these key terms were a bit of a challenge for you, you might want to revisit your hardware notes from last year and then continue with this lesson. Now, we're going to move beyond von Neumann architecture that we've covered so extensively at IGCSE and AS level. And the reason is that modern advances in computer technology have led to a much more complex processor designs. But throughout this design journey, two philosophies stand out, and they are RISC and CISC. Now, these two philosophies, which have emerged over a number of years, are led by programmers and developers who want to emphasize on the hardware that is being used. So they want to mimic whatever high-level languages are doing and create logic circuitry in the hardware that mimics their operation. So if you've got a complex operation in Python, you'll probably have a hardware circuit that can easily execute that. And then you have programmers and developers who want the emphasis to be on the software side of things. So they want to simplify commands, so more work needs to be done by the compiler, and the hardware could be simplified. That means it's cheap to produce, generates less heat, and so forth. So the first philosophy, where you're focusing on the hardware side of things, where hardware becomes complex, you have more logic, more circuits, that's CISC, complex instruction set computer. And the second philosophy, where you simplify things, is called RISC, reduced instruction set computer. But before we begin talking about that, we need to understand what instruction set architecture actually means. So instruction sets, or ISA, instruction set architecture, is a set of basic instructions that a processor understands. This particular instruction set is a portion of what makes up an architecture. So the architecture is the hardware plus this instruction set. Both CISC and RISC will have their own architecture, and both of these architectures will have their own pros and cons. So before we go into that, let's define the architecture of a processor. Now, it involves having the instruction set, the instruction format, addressing modes, and whatever registers are available and accessible by the instructions. So different types of processors will have different types of commands available in the instruction set, different formats, different addressing modes, and various different types of registers. Some will have a lot of registers, others will have a few registers, and that depends on the design philosophy. So starting with CISC, or the complex instruction set computer, makes use of more internal instruction formats than RISC. The design philosophy is to carry out a given task with as few lines of assembly code as possible. So the processor hardware must be capable of handling more complex assembly code instructions. Essentially, CISC architecture is based on single complex instructions which need to be converted by the processor into a number of smaller sub-instructions to carry out the required operation. So in order to do that, they have very large instruction sets, and some of those instruction sets are above 300 plus separate instructions, which make the circuitry very, very complex. And Intel i7 or the x86 range is an example of that. Now, since CISC is rooted into the history of computing itself, in the early days, RAM used to be very limited, so a lot of the heavy lifting had to be done by the processor. So as CISC processors were designed and as they became more complex, equally other areas started to become more complex. You needed to have more specialized addressing modes and more registers were needed. And the complexity of the processor hardware and architecture meant that CISC chips were very difficult to understand and program for. And that meant that they were also very expensive to produce. Now, because CISC processors try to mimic complex software instructions that perhaps have multiple steps, by creating the hardware circuitry, they tend to include more logic, more transistors, and that's one of the reasons they generate more heat. And their size is often bigger, so that means they can't fit into mobile devices. And also the complex instructions themselves might require multiple clock cycles to execute because they are complex instructions, so they have to be broken down into sub-instructions which need to be executed per clock cycle rather than taking 10 clock cycles. So a CISC processor might not know the result of an instruction till 10 or 50 clock cycles compared to a RISC one. However, the benefit of this philosophy is that this leads to shorter coding because you can take one instruction, so the programmer types one instruction and the processor does all of the heavy lifting. RISC, on the other hand, which stands for Reduced Instruction Set Computer, came about in the mid-1980s courtesy of IBM. The idea here was that the best way to improve performance would be to simplify the processor workings as much as possible. So RISC processors have fewer built-in instruction formats. This can lead to a very high level of processor performance. The RISC design philosophy is built on the use of less complex instructions, which is done by breaking up the assembly code instructions into a number of simpler single-cycle instructions. Now, since the instructions are simplified and are of fixed length, that means addressing modes are simplified as well, which means that the circuitry becomes less complex, which means it becomes cheaper, generates less heat, and that led to the rise of ARM processors and M1 and M2, thinner mobile devices, Snapdragon processors, or you name it. The key here, though, was that the instruction set itself had fewer instructions, 100 or less, compared to the 300 plus in CISC. And as a result of that, fewer transistors were used to produce the processors, which meant that RISC chips were cheaper to produce, and they could execute instructions more quickly, potentially allowing for greater speeds. But due to the simple instructions, that meant there was a greater burden placed on the software itself. Less instructions meant you needed to have efficient writing of software and a very efficient compiler. Now here I would like to discuss the need for a control unit, because while a program is being executed, the CPU is receiving a sequence of machine code instructions. So it's the responsibility of the control unit within the CPU to ensure that each machine instruction is handled correctly. The control unit has to read every instruction in turn. So most of the time it's probably hardwired and contains circuit only, but control unit can also contain a ROM chip which contains microcode or the firmware, which is basically an updated instruction set. So what you're probably finding is that modern computers allow the CPU's microcode or instruction set to be updated, so the manufacturer can add more features over time. Now, the CISC processors were designed to suit the compilation of high-level languages, and the RISC processor was introduced as an improvement on these original CISC processors. Now, there are many features for RISC processors, and they include fewer instructions, simpler instructions, single cycle instructions if possible, fewer addressing modes, less memory addressing, and multiple register sets. Now let's do a practical comparison. Do pause the video and study this. On the right is a diagram representing the storage scheme for a generic computer. The main memory is divided into a grid of 6 by 4. The execution unit is responsible for carrying out all the calculations. However, the execution unit can only operate on data that has been loaded into one of the 6 registers. Let's say we want to find out the product of 2 numbers. One is stored in location 2, 3, and the other is stored in location 5, 2. Once we work out this calculation or this multiplication, it then needs to be stored back into 2, 3. So we're basically multiplying 2 numbers in memory. So hopefully you understand the context. Now, using the CISC approach, the primary goal of the architecture is to complete a task in as few lines of assembly code as possible. So what we do is we build the processor hardware that's capable of understanding and executing a series of operations. And for this particular task, a CISC processor would come prepared with a specific instruction which is called mult or multiply. And when we execute this instruction, it loads the 2 values into separate registers. So 2, 3 might go into A, and 5, 2 might go into B. It then executes by multiplying those 2 values and stores the product in an appropriate register, let's just say C. And finally, it takes the value from C and puts it into 2, 3. Thus, the entire task of multiplying 2 numbers can be completed with a single instruction, mult 2:3, 5:2. Pretty straightforward from the programmer's perspective, because all of the heavy lifting, all of the breaking down of the task is done by the processor. So mult is what's known as a complex instruction, and it operates directly on the computer's memory banks and does not require the programmer to explicitly call any loading or storing functions. So it closely resembles a command in a higher level language, for instance. Now, the advantages of this system are that the compiler has to do very little work to translate a high level language statement into assembly. The length of the code is therefore relatively short, which means very little RAM is required to store instructions. So for a CISC approach, the emphasis is put on building complex instructions directly into the hardware itself, which makes life pretty easy for the programmer. Now, the RISC approach is slightly different. Since RISC processors only use simple instructions that can be executed within 1 clock cycle, thus the mult command described previously could be divided into 3 separate commands. Load, which moves data from a memory bank to a register. Product or prod, which means find the product of 2 operands in the registers, and store, which moves data from a register to the memory bank. So the program now becomes something like this. Load into A the value which is stored at 2:3, so load A, 2:3. Similarly, load B, 5:2. Prod A and B, because those 2 registers store those values from memory, and store whatever's in A into 2:3. So we've now got 4 instructions instead of that 1 instruction. Because there are more lines of code, more RAM is needed to store the assembly level instructions. The compiler must also perform more work to convert a high level language statement into code of this particular form. So all of this looks inefficient. However, because each instruction requires 1 clock cycle, separating commands such as load and store reduces the amount of work done by the processor. This actually leads to faster processor performance, since there are ultimately a smaller number of instructions than CISC. Remember, getting to those instructions takes time. Decoding mult into basic sub-tasks or sub-operations takes time. All of that means that the execution time for a complex instruction like mult is longer than the equivalent RISC instructions. So the advantages of RISC are that less logic is required, you end up with cheaper processors, less heat is generated due to a lesser amount of transistors, simplified logic leads to faster execution times, and finally, smaller fixed length instructions rather than the complex variable length ones in CISC. However, there are some disadvantages. RISC uses RAM very heavily, and there are limited addressing modes. So summarizing what we've discussed about CISC and RISC philosophies, there is a greater emphasis on hardware for CISC architecture styles, whereas the emphasis is on software for RISC. For CISC, there are many instruction formats which are possible, whereas RISC uses fewer instruction formats. And similarly, there are a lot more addressing modes available in CISC, whereas there are fewer addressing modes for RISC processors. CISC processors use extensive use of microprogramming because that instruction needs to be broken down into sub-instructions, so that complex instruction is broken down, whereas with RISC, the complexity lies with the compiler because the instructions are very simplified, so the compiler has to deal with more instructions as a result of that. Also, instructions take a varying amount of cycle time for CISC processors because one complex instruction might last a number of cycles, 10, 50, 200. That depends on the instruction itself. Whereas with RISC instructions, everything almost always takes one cycle. Pipelining is difficult for CISC, pipelining is very easy for RISC, and we're going to be discussing pipelining in a bit more detail, so leave this one here for now. And these are most of the common differences that you will encounter. Of course, there's others that you could include, like RISC processors require fewer transistors compared to CISC. Decoding of instructions is more complex for CISC compared to RISC. RISC uses more general multi-purpose registers compared to CISC. And that should be more than enough for you to get the marks in an exam question. Let's now look at how pipelining works. We mentioned pipelining a moment ago. Well, pipelining is something that RISC processors do very well and CISC processors don't do much of at all. Saying that, modern CISC processors are often hybrid processors and they can also tackle pipelining, but we'll leave that for now. So pipelining is basically a standard feature in RISC processors, and it's much like an assembly line. Now, because the processor works on different steps of the instruction at the same time, therefore we can cleverly execute more instructions in a shorter period of time. And how can we do that? Well, if you look at a typical fetch execute cycle, it's split into 5 stages. Now, you might know from IGCSE that you've got fetch, decode, and execute. However, what happens is you fetch the instruction, you decode the instruction, you fetch the operand, then execute the instruction, and finally you write back the results to whichever register or memory location you need to. So there are 5 steps. Of course, modern processors have even more steps than that, 8, 16, and all forth, but these 5 are the most common. And for exam purposes, if you can just remember these, that would be great. Okay, let's look at how pipelining works through a laundry analogy. Let's say that there are 4 loads of dirty laundry that need to be washed, dried, and folded. The washer takes 30 minutes, the dryer takes 40 minutes, and then it takes us 20 minutes to fold the clothes. Now, once we do that, we then pick up the second load, we wash it, we dry it and fold it, and we repeat it for the third and fourth loads. Now, if we started at 6 p.m. and worked as efficiently as possible, we would be still doing laundry until midnight, because it takes us 90 minutes, which is an hour and a half, to do one set. Then the next one takes an hour and a half, then the next one takes an hour and a half, and then the next one takes an hour and a half. So if you started at 6, you've got basically 6 hours. That takes you to midnight. Hopefully that makes sense to you. If you're not sure, have a look at the diagram, and that should work. Now, in an exam, you might need to fill a similar diagram, but instead of laundry and A, B, C, D, you're actually going to be given the fetch execute cycle headings. Anyway, let's continue. So instead of doing this long-winded approach, a smarter approach would be to put the second load of dirty laundry into the washer after the first was already clean and put into the dryer. Then while the first load was being folded, the second load would dry, and the third load could be added to the pipeline of the laundry. And using this method, the laundry would be finished by 9:30. So on the left-hand side, you see the original diagram, and on the right-hand, you see this modified diagram. So you can see what's happening is that when A is in its drying mode, we put B into the washer. And when B is in the drying mode, we put C into the washer. So basically, we've now suddenly become more efficient, and instead of finishing by 12, we finish by 9:30. Now you can see another problem. All of these tasks, washing, drying, and folding, are of different time lengths. What if we were clever enough to ensure that everything was fixed length, for example, 25 minutes or 30 minutes? That would make us even more efficient. And that's where a RISC processor pipeline comes into play. So RISC processor pipeline operates much in the same way, and different processors have different numbers of steps, and these steps are basically the variation of the 5 we discussed earlier. So here's some for the MIPS R3000 processor: fetch instructions from memory, read registers and decode, execute the instruction or calculate an address, access an operand, write the result into a register. Kind of similar to what we were discussing earlier. And modern processors obviously will have a lot more complex steps. So some might have 8, some might have 16, but most of those are going to be variations of these 5 or add more detail into the process. Now, if we come back to that problem that we were discussing a moment ago, when we had variable instruction length, although the washer finishes in half an hour, the dryer takes an extra 10 minutes, and thus the wet clothes must wait 10 minutes for the dryer to free up. The length of the pipeline is dependent on the length of the longest step. Now, because RISC instructions are simpler than those used in CISC processors, they are more conducive to pipelining. While CISC instructions are varied in length, RISC instructions are all the same length and can be fetched in a single operation. Ideally, each of the stages in a RISC processor pipeline should take 1 clock cycle, so that the processor finishes an instruction each clock cycle and averages 1 cycle per instruction, or CPI. Now, what we've just discussed is just basic pipelining, and there are lots of different versions of optimizing pipelines. And these are all optional, and you don't need to study this for A2 level. However, if you're interested in it, it's there for you. One of them is super pipelining, which refers to dividing the pipeline into more steps. So the more pipe stages there are, the faster the pipeline is, because each stage is then shorter. So ideally, a pipeline with 5 stages should be 5 times faster than a non-pipeline processor. The instructions are executed at the speed at which each stage is completed, and each stage takes 1/5 of the amount of time that the non-pipeline instruction takes. Thus, a processor with an 8-step pipeline will be faster than a 5-step counterpart. Now, we're talking about steps which were longer than the 5 that we were discussing for the fetch execute cycle. Well, the MIPS R4000 chops it into more pieces, and you can read some of those on screen. And as you can see, probably that the instruction is divided into 2 steps and the cache access and so forth. But most of those steps are basically similar to the initial 5. Now, this part is also optional. So once somebody thought pipelining and super pipelining were effective, then somebody even more cleverer came along and said, well, okay, what about superscalar pipelining? Instead of having one pipeline, let's have multiple pipelines and have them running in parallel. So the internal components of the processors are replicated, so it can launch multiple instructions in some or all of the pipeline stages. And many of today's machines attempt to find 2 to 6 instructions at the same time, and it can execute them at the same pipeline stage because you can have multiple processors. So think about quad-core, octa-core, and all sorts of things. If some of the instructions are dependent, however, only the first instruction is issued and the rest have to wait once the first instruction is actually executed. And this is where you end up having a stall, and then somebody clever came along and said, well, why not have dynamic pipelines which have the capability to schedule around stalls, and that becomes even more complicated. So the dynamic pipeline is divided into 3 units: the instruction fetch and decode unit, 5 to 10 execute or functional units, and a commit unit. And each execute unit has reservation stations which act as buffers, and they hold commands. So you kind of, in effect, have a mini processor within a processor, that kind of approach. And it gets more complicated than that. So all you need to know is that these dynamic pipelines are even more efficient at executing multiple commands, and the issues that come across when you are looking at superscalar or traditional pipelining are eliminated here through the use of buffers within a pipeline stage. Now pause the video and do read about this, but do remember this is entirely optional. What is not optional is the ability to handle interrupts. Now, an interrupt is a signal sent to the processor from a hardware device, and it can also be a software, but we're only interested in hardware in this particular segment. So the interrupt suggests that the device requires attention, and normally a processor will halt its current task and enters an interrupt service routine, and then that deals with the interrupt, and you never realize that the program was interrupted in the first place. Now, interrupts provide a very efficient means of control, since the processor doesn't have to be responsible for regularly checking the status of every single hardware device it's connected to. Instead, it can concentrate on executing code or whatever else its current main task may be. It only deals with the hardware devices when necessary. But with pipelining, there is an additional degree of complexity, because when an interrupt is received, there might be several instructions in the pipeline. So in a pipeline system, one option for handling the interrupt is to erase the entire pipeline's contents, and then the normal interrupt handling routine can be applied to the remaining instructions. The other option is to construct the individual units in the processor with individual program counter registers. So you have more registers, so you can work out which stage each instruction was and save those contents into the registers and restore them when the ISR is finished dealing with the interrupt. Now this allows current data to be stored for all the instructions in the pipeline while the interrupt is handled. Mostly though, as is the cheaper option, all instructions are discarded except for the ones which might be in the write back stage because they are written to first, and then the remaining instructions are discarded, the interrupt is handled, and then all those remaining instructions are reloaded. Okay, that's enough for now. Let's see if you can apply your knowledge and answer some of these questions. So do pause the video and go through these questions, write the answers, and get back to me. Part B would require you to do some additional research. So you might need to look at this online, but it's pretty straightforward. You should have guessed the answer by now, why they're hardwired. But if you're not sure, just a quick search online would get you the results. Okay, that's it for now. You should be able to tell what the difference is between RISC and CISC design philosophies. You should be able to explain how pipelining works. You should be able to give examples of a complex instruction. And you should be able to explain how an interrupt is handled by a RISC processor. Now, if you do have any questions, please do get back to me. Otherwise, that's it for now, and I'll see you in the next one.